Hello, my name is DOrlando, and today I'll be walking you through my course project, which centralizes around predictive versus realized vulnerability analysis. This project examines how well predictive models align with realized exploitation of vulnerabilities and exploits using two major cybersecurity datasets using EPSS and EVD. The central research question for this study is, does the predictive nature of vulnerability priority align with realized vulnerability exposure? In other words, how do CVSS severity scores from the NVD database compare with exploitation likelihood scores from EPSS, meaning is what we're predicting matching what's happening? By combining these two data sets, we can really identify whether current predictive processes help organizations and agencies prioritize patching effectively. To answer this question, I integrated complementary data sets using CVE IDs as a shared key for a 30-day period, which is really the month of September of 2025. Together, these data sets let us compare the severity with real-world exploitation and the probability predicted on whether that exploit is going to be a problem. So the raw data from both these data sources required significant cleaning and integration. So in Python, I pulled both data sets using APIs, standardized the fields, removed the duplicates, and merged them into a single CSV. After all the significant cleaning and data, wrangling, it came up to about 15,000 rows for a single month period. This data set was then imported into Tableau, where several calculated fields to support the analysis were created, which then were transposed into 5 charts, with really 3 serving as the foundation of the analysis. So the analysis in Tableau used several techniques, each designed to highlight a different aspect of this problem or this question. A scatter plot comparing CVSS scores to EPSS likelihood, a risk matrix heat map showing vulnerabilities across severity and likelihood bins, a cluster analysis incorporating age and vulnerability percentile overlaid onto the scatter plot, and then a CWE to product heat map to identify weaknesses and trends across products. I also then went on to create a prioritization table based on this data to really kind of create a remediation patching queue, which I'll get to in a minute. So the scatter plot revealed both kind of expected and surprising results. Many of the vulnerabilities fell into high CVSS and high EPSS. This really shows a strong alignment between what we're predicting and what is being exploited, which is a good thing. It means that these cybersecurity agencies are doing a good job. There were outliers that exist, really on two ends of the spectrum, where one had a high EPSS score, or several had a high EPSS score, but a low CVSS score, meaning that there was something that we predicted that was going to be a big problem, and then it didn't end up being. This was centralized around niche products that just aren't really mainstream, which does make sense because hackers go for more commonly used technologies. Conversely, some vulnerabilities had a high CVSS score, but a low EPSS score. What's interesting, though, is many of these were still patched in time to not become a big problem, which reflects how, even if we're not predicting these security exploits are going to be a big problem, many organizations and agencies are defaulting on the side of higher security. So the cluster analysis added some depth to how the factoring in of age and vulnerabilities really organized into 3 clusters. This was due to many entries were present. Due to how many entries were present, I used Microsoft as an example. Most clusters still showed positive alignment between CVSS and EPSS, but for Microsoft specifically, SharePoint stood out as a outlier where several vulnerabilities remained unresolved far longer than expected, even when there was a high predictive and severity score, really both flagging them. So this kind of highlights the blind spots that predictive models and even vendors have out in the real world. So next, the risk matrix shows that most vulnerabilities were medium or high severity, but low likelihood of exploitation, which is encouraging. It means that there's a high correlation between the two, and they're doing a good job. However, medium level vulnerabilities appeared under-resourced, which shows a potential blind spot in patching strategies. To support this even further, the CWE to product heat map highlighted reoccurring weaknesses across product families. Again, using Microsoft because they have a lot of software. They're very common now in the technology space. Their product line specifically showed broad coverage, but again, SharePoint came up as an outlier with concentrated CWE vulnerabilities in the medium to severe category that were unaddressed. So moving on to the prioritization table, this emulated a remediation spreadsheet, really the kind of basis to develop those by ranking each vulnerabilities using combined severity, likelihood, SLA status, and the different alignment categories that we created in the calculated fields. This created a practical patching queue. Notable findings in here was, high priority items like WordPress plugins, FTP software, and certain router exploits that had remained unpatched for the entire 30-day period of September. For Microsoft specifically, the table flagged privilege escalation points that really had to do with SharePoint and certain network access issues that weren't fully predicted by EPSS and remained as an outlier and should be a priority. From this analysis, it really shows a few things. Predictive models like EPSS align well with realized risk, but they're not perfect. Medium to critical vulnerabilities are often overlooked despite volume. Vendor blind spots do exist. SharePoint was a good example in this case for this particular month. And remediation sheets that are out there today that different agencies use could be more refined using analytical models like this between already used public data sets. However, this study was limited to a 1-month time frame and only 2 data sets. I mean, there are other data sets that can contribute to it, and it simplified the SLA assumptions to a 30-day period. Expanding the time horizon, incorporating some additional data sources would greatly improve the reliability and depth of this study, and also possibly require parallelization and computing to really accomplish. So in summary, this project demonstrates the value of combining predictive and descriptive vulnerability data to improve prioritization. By aligning CVSS, EPSS, and even potentially in the future other data, we can improve security postures, identify blind spots, and guide more effective remediation strategies. Thank you.